Okay, so we're live. Well, welcome everyone to another TCS Plus talk. We're very happy today to have Santhoshini Velusamy from Harvard University, who will tell us about approximability of all finite Max-CSPs in the dynamic streaming model. Now, before we begin, let me just thank the rest of the organizers, which include Clement Kanan, Rachel Cummings, Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Noah Stevens Davidowitz, Tomas Vidik, and David Weiss. I'll mention that I'll be monitoring the chat, so feel free to ask questions through there. You can also unmute yourself. And I do want to encourage people to keep their cameras on to give Santhoshini some visual feedback throughout the talk. But with that being said, Santhoshini, please take it away.
Great. Thank you so much, Eric, for the introduction. Hi, everyone. Thanks for coming to the talk. I'm Santhoshini. I'm a third-year graduate student at Harvard University, advised by Madhusudan. Today, I'll be talking about our recent work on characterizing the exact approximability of every finite Max-CSP in the dynamic streaming setting. This is joint work with my amazing collaborators, Chining, Sasha, and Madhu, and who are here with us today. At any point during the talk, please feel free to unmute yourselves if you have any questions. Great, let's get started. So today I'll be talking about maximum constraint satisfaction problems. These are an important class of optimization problems, which include problems like Max-CSP, Max-DICUT, Max-KSAT, unique games, etc. Before I formally define this class, let me motivate with a simple example, Max-CSP. In Max-CSP, you are given an undirected graph, and the goal is to find a bipartition that maximizes the number of edges that go across. In this case, the red bipartition shown here is the best bipartition, and it corresponds to a cut size of 4. Now, let me show you how we will frame this as a CSP problem. So we have variables, x1, x2 to x4, corresponding to each vertex, and these variables are going to take an assignment 0 or 1. Notice that every such assignment corresponds to a bipartition in the vertex set. This is because you can simply take the variables assigned bit 0 and put the corresponding vertices in one set and put the remaining vertices in another set. That is a natural bipartition. Now, here's the constraint function. So I call it the fcut function. It takes as input 2 bits x and y and outputs the XOR. Now, corresponding to each edge in this graph, ij, we create the XOR constraint, xi, XOR, xj. Now, this is the whole instance. You have variables and you have a bunch of constraints. The task is to find the best assignment to these variables that satisfies the maximum number of constraints, as many as possible. And how is this related to Max-CSP? So observe that an edge is going to lie across the bipartition defined by this assignment to the variables, if and only if the XOR of the corresponding vertices evaluates to 1. And that's exactly what we are capturing here. And in this case, one of the best assignments is the one shown here, and that corresponds to the bipartition on the left. Any questions here? Okay, good. So now I'll go ahead and define the formal, give the formal definition for Max-CSPs. In general, we have a finite family of constraint functions, F1 to Fr. And here we can think of each constraint function as a k arity function, which basically takes as input k variables and is going to give a 0 or 1 output. It's also okay if you have functions with different arities, but always you can introduce some dummy variables to make sure that every function is of the same arity. And that's what we will consider here. So again, you have variables x1 to xn, and each xi is going to be assigned some value in the domain. Because the domain is finite, without loss of generality, you can just assume it's q. So what's an instance of Max-CSP? It consists of constraints applied on sequences of k distinct variables. What do I mean by this? So for each constraint, we pick one of the constraint functions f1 to fr, and then pick a sequence of k distinct variables from this set and apply the constraint function on that sequence. The goal is to compute the value of the instance, which is defined as the maximum fraction of constraints that can be satisfied by any possible assignment to these variables. For the purpose of this talk, I'll be mostly focusing only on single Boolean constraints. Let's take a look at them. So here, the family consists of a single Boolean constraint. And by Boolean, we'll assume that the domain is plus minus 1. Variables are again going to be x1 to xn, but we also have literals now. You have x1 to xn and minus x1 to minus xn. These are the literals. Now here, the instance is defined as the constraint f applied on sequences of k distinct literals. And here again, the goal is to compute the maximum fraction of constraints that can be satisfied. Okay, so now let's take a look at another example to familiarize with the framework. Here's the truth table corresponding to the to and function. Here's an example of an instance of max to and that's defined on 3 variables with 4 constraints. In this case, the best assignment turns out to be the following, where x1 is assigned 1, x2 is assigned -1, and x3 is assigned -1. You're able to satisfy, I guess, the second constraint and the last constraint, but that's all. The first and the third constraint are not satisfied. And you can just manually check that this is the best possible. And in this case, the value of the instance is just half. Okay, so now let's look at these maximum constraint satisfaction problems in the streaming setting. What is the streaming setting? First, I'll define the most simplest notion of the streaming setting, which is the insertion only setting. Here, constraints are added one by one in a stream. So think of these dots here as the variables that are predefined. And now in each time step, you're adding some constraints. In this example, these constraints are just arity true constraints applied on just 2 variables. So you're adding constraint E1, E2, E3, E4, and so on. This is how the streaming model looks like. Now let's consider the dynamic streaming setting. In this case, you can either add a constraint or delete a constraint in each time step. Let's look at an example. E1 is added, E2 is added, E3 is added, but now E2 is deleted, and then you add E4. And the resulting constraints are just E1, E3, E4. So what do we want a streaming algorithm for Max-CSP to achieve? Given an instance psi of a Max-CSP, we want the algorithm to compute value of the instance psi. But the challenge for the algorithm is that it's allowed to use only space that is polylogarithmic in n. We do not worry about the dependence on k, the arity of the constraint, or dependence on r, the number of different constraint functions. But what we really care about is only the dependence on n, which is the number of variables. And using only this much space, the streaming algorithm is supposed to compute the value of the instance. Is the problem statement clear? Okay, so for most function families F, the exact computation of the optimum is hard. So we are interested in computing, or we are interested in getting alpha approximation algorithms, which are expected to do the following. On input side, which is an instance, with high probability, we want the algorithm to compute a value V such that this value is at least alpha fraction of the value of the assignment psi and is upper bounded by value of psi. So this is what we are looking for the Max-F problems. In this work, we actually study a more refined notion of approximability. Basically, for every gamma, which is strictly greater than beta, we want to understand the answer to the following question. We call this the gamma beta Max-F problem. And then it asks if it's possible to distinguish instances with value at least gamma from instances with value at most beta with high probability. And we want to, again, answer this question in this entire range shown here. Okay, now let me describe our first main result. This is a dichotomy theorem to characterize approximability of every finite CSP in the dynamic streaming setting. So for this, let's look at the gamma beta Max-F problem. We define a property Pf, which depends on the function family f, such that if this property is satisfied with parameters gamma and beta, then we show there is a dynamic streaming algorithm that can solve gamma beta Max-F. On the other hand, if the property is not satisfied, then we show that essentially you cannot solve gamma beta Max-F, or in other words, for every epsilon greater than 0, every dynamic streaming algorithm that solves gamma minus epsilon beta plus epsilon Max-F requires at least square root of n space. Is the dichotomy theorem clear? So basically there is a property. If the property is satisfied, you are able to solve the problem by defined earlier. And if it's not satisfied, you basically cannot solve the problem. And this is the dichotomy. Okay, here's our second main result. This is in the insertion-only streaming setting. And it's a weaker result where we give a sufficient condition for showing approximation resistance of some CSPs. Before that, I need to define what I mean by approximation resistance. Let's take a look at it. So let's say the constraint family consists of a single constraint function. Then we define rho of f to be the probability that a uniform random assignment satisfies a constraint of f. For example, let's take a look at the cut constraint that we had previously. It was simply an XOR constraint. Now, if you take a random assignment to the variables, it's going to satisfy this XOR constraint with probability half. And so rho of f cut is just half in this case. Observe that from this definition, it follows that value of any instance psi, where psi is an instance of max f, always lies between rho of f and 1. So you have a trivial rho of f approximation algorithm where you simply just output rho of f as your answer. And we show that if this property is not, the property PF is not satisfied when you substitute gamma to be 1 and beta to be rho of f, then max f is indeed approximation resistant. And what this means is that apart from the trivial approximation algorithm, you have nothing that performs better in the streaming setting. There is no rho of f plus epsilon approximation algorithm for any epsilon greater than 0. This notion of approximation resistance can also be extended to families of functions. So here's the outline for the rest of my talk. First, I'm going to talk about prior works. Then I'll cover our first main result, which is the dichotomy theorem in the dynamic streaming setting. Then I'll cover the second main result in the insertion-only streaming setting. Finally, I'll conclude with a couple of open problems. Any questions so far?
Okay. I guess maybe you'll cover this later, but is a root n like considered like, is there an easy solution that can always get root n, or is that just the?
Oh, that's a very good question. No, not really. So it's not that we know that there is a better approximation algorithm if you give me root n space or something. For example, if you take Max-CSP, in fact, I'm going to talk about it. Max-CSP is approximation resistance in a very strong sense. Like, even if, so unless I give you linear space, you cannot do better than half approximation. So this root n space bounds usually come from the communication lower bound, where in the communication game, if there are more than square root of n bits of communication or something, then the problem is easily solvable. But it's not like a fundamental, how do I say, a fundamental lower bound for the streaming problem itself. Does that answer your question?
Yes, thanks.
Cool, thanks. Great. Again, so we're going to talk about the Max-CSP problem now. So as I discussed earlier, the rho for the cut constraint is just half. And the first work of Caprillo, Khanna, and Suthan show that, in fact, Max-CSP is approximation resistant. They prove a square root of n lower bound, basically showing that any streaming algorithm that performs better than a half approximation requires square root of n space. But this bound was later improved a lot. And finally, the work of Caprillo and Krachon shows that, in fact, you even need linear space to perform better than half approximation. And all these lower bounds stem from the fundamental fact that in the streaming setting, it is very hard to distinguish between random bipartite graph and a random graph. And this is what leads to these strong hardness results. The second Max-CSP problem that was studied in this setting is the Max-2 problem, which we saw earlier. Again, if you consider a uniform random assignment, it's going to satisfy an AND constraint with probability 1/4. And so rho of F2 AND is 1/4. So there was this question of whether is Max-2 AND is also approximation resistant. And in these works, we showed that, in fact, you can beat the trivial 1/4 approximation for Max-2 AND. There is something non-trivial that you can do for this problem in the streaming setting. In the first work with Venkat and Amaya, we showed that it is possible to get a 2/5 approximation algorithm. In later works with Cheening and Sasha, we in fact improved it and showed that we can get a 4/9 approximation algorithm. And we also showed that this is optimal. Any streaming algorithm that beats it is going to require at least square root of n space. Okay. Now I'm going to discuss this algorithm, which I call the bias-based algorithm in detail. Okay, there's a question from Yarek. I'm not able. Yarek, can you ask the question? Disappeared. Oh, sure. Yeah.
Yarek, can you unmute yourself? I can read also the question now.
Anything is fine. I'm just not able to see the chat box.
So we can't hear you, but I can read the question out. So
sure.
Yarek is asking, do you know any CSP that has sublinear space algorithm for some approximation, but not polylog? Or is there a chance that all those approximation resistant problems require linear space?
That's a really, really good question, because that's another work that we are currently doing. And yeah, it seems like it might be possible that. So right now, yeah, we do not actually know the answer to this question, whether there is a CSP for which you have non-trivial approximability, but it could be possible. For example, even the Max-DICUT, my personal take, I think Max-DICUT problem or the Max-2 AND problem itself could be a good candidate. We do not see a path to show linear space lower bound for this particular problem. And there is some evidence that all the hard distributions basically that we have in the square root of n space lower bound, when you give slightly more than square root of n space, we are able to distinguish these distributions. So yeah, it is very possible that Max-2 AND or DICUT could be such a candidate. Does it answer your question?
Yes.
Okay, cool. All right. So I'm going to discuss this bias-based algorithm for Max-2 AND in detail. This is because we are going to later see that this is going to form the basis for every optimal algorithm that I'm going to describe for any finite Max-CSP. So we're going to go over this in detail, and then I'll show you how to extend this for other CSPs. Okay. So the first thing is that we define a bias vector, which is an n-length vector, and each component of this vector corresponds to a particular variable. And what does this component measure? Let's look at the ith component. The ith component basically measures the difference between the number of constraints that contain the positive literal versus the number of constraints that contain the negated literal. That's all. This is the bias, ith bias component, and it also has some scaling factor. Now, the total bias of the instance is defined as the L1 norm of this vector multiplied by 1 over m. And this scaling is just because we think of value of an instance as the fraction of constraints that are satisfied, and which is why bias also has the corresponding scaling, but that's not too important. So bias is essentially the L1 norm of the bias vector. Now, the key idea behind both these works is that bias non-trivially approximates the value of the instance. In the first work with Venkat and Amaya, we showed the following relation between value of the instance and the bias of the instance. And the algorithm was very simple. We simply computed the bias of the instance in a streaming way, and then outputted max of 1 over 4 and the bias of the instance. And just from these relations, it turned out that this was a 2/5 approximation algorithm. In the later work with Cheening and Sasha, we showed that, in fact, you can do better than just the trivial 1 over 4 lower bound in low bias regions. And we showed when the bias is very small, you can prove this following improved lower bound on the value of the instance. And the algorithm, again, was if your bias is high enough, you simply output it. And if the bias is low, output this as the proxy for your value. And this gave us the 4 over 9 approximation algorithm. Any questions on this slide? Okay. So how do we estimate this bias? So now I've hopefully convinced you that at least for the Max-2 AND problem, if you manage to estimate bias, then you get a pretty good estimate of what the value of the instance should be. But how do we estimate this bias? So these works by Indic and Kane et al. Show that it is possible to estimate the L1 norm of a vector when at each time step, you're just doing a bounded update to one of its coordinates. And all this can be achieved in polylog and space. So if you look at the bias vector, you can think of it as the following. So you have this bias vector where each component just measures the difference between the number of positive and the number of negated literals of that particular variable. Now, at each time step, you get a constraint. Now, let's say the constraint is xi minus xj. At that point, you maintain this big bias. I mean, it's not that you actually do it in the streaming setting, but let's imagine that you're maintaining this big bias vector. Then you're going to update the ith coordinate by +½ and the jth coordinate by -½ And in the end, the resulting ith coordinate is exactly this component bi. So if we compute the L1, so we can use this algorithm of Indic et al. To compute the L1 norm of this bias vector, which is what we need to compute the bias of the instance. Okay, so now I'm going to talk about our first main result in detail, which is the dichotomy theorem for dynamic streams. Okay, so again, let's recall. We want to answer the gamma beta max F problem, where we want to distinguish between instances that have value at least gamma versus instances with value at most beta. Now, we define a property, and this is what we saw. We define a property such that if it's satisfied, then there is a dynamic streaming algorithm. And if it's not satisfied, then you don't have a dynamic streaming algorithm. Now, let me get into a little bit more detail on what this property is. So basically, we define two convex closed and bounded sets. One is the K yes gamma set, and another is the K no beta set. These sets depend on, of course, they depend on the function family F. Here's our dichotomy theorem in terms of these sets. When these sets are disjoint, this is when the property is satisfied, we show that it is possible to solve gamma beta max F. And when these two sets overlap, we show that it is not possible to solve gamma beta max F. This is essentially our dichotomy theorem. By the way, in this talk, I'm actually not going to give the full definition of what the sets Ks and Kno are, but I'm going to motivate these, how these sets are defined in such a way that we get this cool dichotomy theorem. Okay, so now I'm going to talk about the algorithm for solving gamma beta max F when the yes sets and the no sets are disjoint. Here, for the purpose of the talk, again, I'm going to focus on single Boolean constraint, but everything I say is extendable also to general constraint families. Okay. When we have two convex closed and bounded sets, we have the following separating hyperplane theorem. Basically, what this theorem states is that you have a hyperplane separating these two closed and convex sets, such that if lambda is the normal of the separating hyperplane, there exist two real numbers C1, C2, such that for all those vectors that lie in, let's say, the yes set, the inner product of V with lambda is at least C1. And for all those vectors that lie in the no set, the inner product is at most C2. Basically, there is a gap when you measure the inner product with either the vectors in the yes set or the vectors in the no set. This is the separating hyperplane theorem. Now let me show you how we use the separating hyperplane theorem to get a bias-based algorithm in this case. So what is the goal? We want to distinguish instance psi from phi, where value of psi is at least gamma and value of phi is at most beta. This is our goal. Now consider the normal of the separating hyperplane, lambda. Here's how we define our new bias vector. So now we have to carefully define what the ith component is. Let's look at the variable xi. And this quantity, pos I of j, represents the number of constraints containing xi in position j. There are k positions because in general you have a k arity constraint. So neg of I sub j is just the number of constraints containing negation xi in position j. We scale this difference with lambda j, where lambda j is the jth coordinate of the lambda vector, and then take this scaled sum. This is how we define each component of the bias vector. Okay. And again, we define the total bias of the instance to be the scaled L1 norm of this vector. The crucial thing we prove is that when value of psi is at least gamma, then the bias of the instance turns out to be at least C1, where C1 comes from the hyperplane separation theorem. And when value of phi is at most beta, then the bias of phi is at most C2. And thus, once we prove these two statements, you can simply again estimate the bias of the instance, and that will help you distinguish whether it's the at least gamma instance or the at most beta instance. Okay, now I'm going to give an intuition behind how these yes sets and no sets are defined in such a way that the bias property that I showed earlier holds. Let's take a closer look at this definition of bias. So bias was defined to be the scaled L1 norm of a bias vector. But there is this another way in which you can write the expression for L1 norm of any vector. So the bias vector, recall, is an n-length vector. You can consider L1 norm, you can consider inner product of these vectors with plus minus 1 vectors of length n. When the vector A is of the form where Aj is just sine of Bj, then you get the L1 norm expression here. You get L1 norm here. And if not, you're going to always get a quantity that's smaller than the L1 norm. So you can write bias as this quantity you see over here, which is max overall. Let me call this as an assignment vector. Max overall assignment vectors, 1 over m times the inner product of this assignment vector with the bias vector. Is this clear? Okay, so now, given this information, I'm going to define a family of distributions on -1 power k. So how am I going to define this family? For every assignment vector, I'm going to define a distribution, which I call d of psi sub a, which is going to depend on both the instance psi and the assignment vector a. Here's how we define the distribution. We sample a random constraint, a k-tuple from psi, and then output the assignment corresponding to a. Let me explain this with an example. It'll make the statement clearer. So let's consider our favorite max-DICUT instance, where you had the following constraints. Now, to get the distribution d of psi sub a, this is what I do. So it is just uniform distribution over all these constraint tuples. You sample a constraint tuple, let's say minus x3, x1. Then I just substitute, instead of x3, I substitute a3 with it, and x1, I substitute a1 with it. And that's all. This uniform distribution is the d of psi sub a distribution. And this notation delta basically is the space of all distributions over -1, 1, 2, part 2. Okay, this is the family of distributions we define. And okay, what was the reason why I defined all these distributions? Here's the key connection. The inner product of the assignment vector with the bias vector turns out to be equal to the following inner product. Inner product of the marginal vector of distribution d of psi sub a with lambda, where the marginal vector of a distribution is just defined to be the distribution, it's just defined to be the vector of first order moments of the distribution. Do you have any questions on this slide? Okay, so rewriting it. So instead of, when I rewrite this using the marginal vector definition, we can just write bias of psi as max overall assignment vectors, the inner product of the marginal vector of the distribution d of psi sub a with the lambda vector. Lambda was the separating normal of the separating hyperplane. So, okay, the way we define the yes sets and no sets is the following. We define them in such a way that if the value of an instance psi is at least gamma, then look at the assignment under which this value is at least gamma. Let's say this assignment is A. Then by the definition, the way we define the sets yes and no, it satisfies that if you take the marginal vector of the distribution d of psi sub A, it belongs to the yes set with parameter gamma. Okay. Now from the separating hyperplane theorem, it follows that the inner product of this vector with the normal of the separating hyperplane is at least C1. So since there exists at least one assignment so that this is true, if you consider the max, which is how the bias is defined, that's going to be at least C1. On the other hand, when value of phi is at most beta, then we show that for every assignment A, this marginal vector lies inside the no set with parameter beta. And in this case, by the separating hyperplane theorem, if you look at the inner product, it's going to be bounded by C2 for every assignment. And hence for the max also, it's going to be bounded by C2. So this is the intuition behind how we define these sets and how that can be used to show that bias essentially separates these two instances. Any questions here? I know that the last couple of slides were a bit notationally heavy, but this was just meant to give some intuition behind how these sets can be defined so that when they are separated, we get a way to separate the original psi and phi instances with the value gamma and beta. Okay, so
is there a way to see what these sets are, say, for the and?
Sorry, can you go again? Sorry.
I'm wondering if there's a simple way or a way to see what these sets k no and k yes are for the and function.
That's a good point. Yeah, right now I haven't included the definition of these sets here, but I think at the end of the talk, I can definitely try and give the definition and see if there's a. So the yes set definition is not too hard to understand, but the no set is slightly harder to motivate. So I'll definitely be happy to chat about it at the end of the talk, if that's okay. Great. Okay, so for extension to general Max-F, in this case, when we have families of constraint functions, we actually need to define a bias matrix. And then we define bias to be the L1 infinity norm of this matrix, whereby L1 infinity norm, what I mean is that you take the L infinity norm of the rows and then L1 norm of the whole thing. That's how we define L1 infinity norm. And this work of Andani et al. Shows that it is possible to estimate L1 infinity norm in the streaming setting using polylog space. And again, the definitions of the sets K yes, K no, and even the distributions can be carefully extended so that the same dichotomy theorem holds. Okay. Now I'll talk about the lower bound for gamma beta max F when the sets overlap. Okay. Here's the dynamic streaming lower bound. When the sets overlap, every dynamic streaming algorithm that solves gamma minus epsilon and beta plus epsilon max F requires space at least omega square root of n. And like all other streaming lower bounds, here again, lower bound is going to follow from communication hardness of a one-way communication game. I'll talk about the communication game now. First, I'll talk about the two-player version of the game. And later, the streaming lower bounds actually come from multiplayer versions of the game, which I'll discuss later. Okay, so we call this the signal detection game. It depends on two distributions, dy and dn. These are distributions over q power k with same marginal distributions in each of the key coordinates. Okay. What is this problem? So we first have Alice and Bob. Alice gets a random q partition of the vertex set or variable set. So let's take an example. Here you have 16 vertices, and this is some random partition of these 16 vertices into 4 sets. Bob gets a random k hypermatching on these vertices. In this example, let's say we take k equal to 3. So, and Bob gets 3 hyper edges, and each of them are just basically triangles. Okay. And the reason why I have color-coded these edges is to show that here's the, okay, so red vertex I would consider as, I want to think of these edges as some sense a directed edge, in the sense that red vertex is going to denote the first vertex, the vertex marked green is the second vertex, and the vertex marked blue is the third vertex. Sorry, I just saw a question on chat. Oh, okay, it's just, okay, great. So,
for the,
yeah,
it's just a link.
Okay, sounds good. All right, so these are the hyper matchings. And now Bob also gets an edge labeling on these edges. So so there are 3 edges and there are 3 bits here, Z1, Z2, Z3. And how are these, what are these bits? So in the yes case, there is a BI that's independently sampled from this distribution dy. And the ZI corresponding to this edge is equal to 1, if and only if the vertex labels of this edge match BI. What do I mean by this? So let's consider the first edge. Its vertex labels are just 1, 2, 3. And this ZI is going to be set as 1 if and only if the BI you sample from dy is equal to 1, 2, 3. In all other cases, it's just going to be set as 0. And in the no case, essentially you're just doing the same process, but the BI is sampled independently from the no distribution, dm. Okay. And what is the task of these two people? Alice is asked to send a single message to Bob. And in the end, Bob has to distinguish whether their instances are from the yes case or the no case. Okay. And we prove that solving this problem requires at least square root of n bits of communications from Alice. This is a communication lower bound that we prove. And for the multiplayer communication game, there are two different kinds of communication lower bounds that we need to prove, depending upon which streaming setting you're looking at. In the dynamic streaming setting, we need to prove communication lower bound in a model where you have a referee. So you think of the same signal detection problem, but instead of a single Alice and a single Bob, you have a single Alice and multiple independent copies of Bob, all correlated with the same Alice. Now there is some referee, and all of these people are required to send simultaneously a single message to the referee. And the referee has to decide whether their instances are from the yes case or the no case. In the insertion-only streaming setting, we prove lower bounds in this communication without a referee model, where again you have Alice and independent copies of Bob. Alice sends a message to Bob, Bob 1 sends a message to Bob 2, and so on. And the final Bob has to decide whether the instances are from the yes case or the no case. So these are the communication games that we use to prove our streaming lower bounds. First, let me talk about the dynamic streaming lower bound. In this case, we are able to prove the following strong indistinguishability theorem. If there exists Max-F instances psi and phi, and assignment A1, A2 such that, let's say under the assignment A1, the value of the instance psi is at least gamma, and value of instance phi is at most beta. That's under any assignment. And the distributions d of psi sub A1 and d of phi sub A2 have the same marginal distributions in each of the k coordinates. Then we show that it's hard for a streaming algorithm to distinguish between psi and phi. It requires at least square root of n space. And the key idea is that when the yes sets and the no sets intersect, we show that it is possible to satisfy the conditions of the strong indistinguishability theorem, and in the end conclude that any dynamic streaming algorithm that has to solve gamma beta max f requires omega square root of n space. This is a good point to ask if you have any questions. Okay, so now I'll talk about our next main result, which is approximation resistance in the insertion-only streams. Here, we are only able to prove a weaker indistinguishability theorem. So in this setting, we show that if you have instances psi and phi and assignments A1, A2 such that the first condition is again identical to the dynamic streaming setting. But the second condition, in addition to requiring that these two distributions have the same marginal distribution, we also need some additional structure on these distributions. So let's do this carefully. So we want the distribution d of psi sub A1 to be sum of two distributions d0 and dy. We also want d of phi sub A2 to be the sum of the same distribution d0 with another distribution dn. They have the same weights. And we expect these dy and dn distributions to have uniform marginal distributions. So a simpler way to think about this condition when you don't have d0 is like, if your distribution d of psi sub A1 and d of phi sub A2, let's say they have the same uniform marginal distributions, then we are able to show that it is hard to distinguish these two instances in the insertion-only streaming setting. Okay. And that's why in this case, we do not get the full range of the dichotomy theorem. But in the specific case, when the yes set with parameter 1 and the no set with parameter rho of f intersect, then we show that it is possible to apply the one rho of f weak indistinguishability theorem and conclude that there is no better than rho of f approximation algorithm for Max-F. So as a corollary, if what we say is that if you have a function family f such that these two sets intersect, then Max-F is approximation resistant. This is our main result for the insertion-only streaming setting. I also want to note here that our weak indistinguishability theorem actually suffices to recover all previously known square root of n space lower bounds for two CSPs in this setting. All right. So we're near the end of my talk. Before I conclude, I want to highlight a very recent application of our results to study a problem that is even not a CSP. This is called the maximum acyclic subgraph problem. And this is based on joint work with Noah Singer, who is an undergrad at Harvard University, and Madhusudan. Okay, what is this problem? This problem asks to find the largest acyclic subgraph of a directed graph. Or in the streaming setting, you can think of the edges of the directed graph being sent one by one in a streaming fashion. And in the end, you want to estimate the size of the largest acyclic subgraph of this directed graph. Notice that this problem is equivalent to finding an ordering of the vertex set that maximizes the number of forward edges. In another sense, consider any ordering of the vertex set. I say an edge is forward if, let's say, the pi of I is less than pi of j, if ij is the original vertex label. Okay, so consider any ordering. Look at all the edges that point forward. They are going to form an acyclic subgraph. Similarly, if you consider any acyclic subgraph, you can give an ordering of the vertex set such that all the edges in this subgraph point forward. So these two problems are equivalent. And even in this, you have a trivial half approximation algorithm. Basically, consider a uniform random ordering of the vertex set. Roughly half, in expectation, half of the edges are going to point forward. So this means that no matter what directed graph you have, you always have an acyclic subgraph of size m over 2. In the classical setting, Guruswamy et al. Show that, assuming the unique games conjecture, you can actually show that MAS is approximation resistant. In the streaming setting, Guruswamy and Tao actually proved the unique games conjecture unconditionally. However, the reduction from the classical setting did not apply in the streaming setting. And the best reduction that they could get only ruled out a 3/4 plus epsilon approximation algorithm for MAS. In this work, we actually show that MAS is approximation resistant using our lower bounds in the insertion-only streaming setting from the CSP paper. Okay, we look at a related CSP, call it FMAS, and we show a streaming reduction from this CSP to the MAS problem. Using our insertion-only lower bounds, we prove that FMAS is approximation resistant for all Q, and this helps us show that indeed, MAS is approximation resistant in the insertion-only streaming setting. I think this is a very cool application of the results for CSPs to understand the approximability of a fundamental problem that is not a CSP. And I hope that even for other related problems, maybe our results could help shed some light on their approximability. Great. Any questions here? Okay, we have come to the end of this talk. I'm going to leave you with a couple of very interesting open problems in this framework. So the first open problem is whether it's possible to get a dichotomy theorem in the insertion-only streaming setting. What are the challenges? So these works of Lee et al. And I et al. Show that dynamic streaming algorithms are essentially linear sketches. And the bias-based algorithm that I defined before can be implemented as a linear sketching algorithm. However, such a result is not known for the insertion-only streaming setting, and it's possible that there could be a better, more complicated algorithm than the simple bias-based algorithm in this setting. It is also harder to prove communication lower bounds in the non-referee setting, which is why we ended up getting the weaker indistinguishability theorem. On the other hand, in the dynamic streaming setting, we could get a very strong indistinguishability theorem. Okay. The second open problem asks if additional passes through the stream help. So let's say you're allowed to take a constant number of passes through the same set of constraints. Is it possible to get an algorithm that beats the approximation factor achieved by the bias-based algorithm? It's not clear if there exists such a CSP, and this problem is wide open. I think Max-2 and or Max-DICUT could be a very potential candidate to investigate for this question, but as of now, yeah, we do not know any answer for this question. That's all. Thank you so much for listening. I'll be very happy to take questions now.
So, okay, I have a question. I guess I'm a little bit, is it clear that linear even is always possible?
That's good. Maybe. So, okay, at least for Max-CUT, you have this sparsification algorithm where you can like sample a bunch of edges. And then like, if you just estimate the cut value of the sparsifier, that's going to give you a good approximation for the cut itself. And even here, I think that's possible. So you just like sample a random set of constraints and then compute, you just like, I don't know, store in linear space and then compute the optimum of that, whatever constraints you have sampled. And maybe, I mean, I think you can prove concentration bound showing that with probably high probability or something, you're going to compute the optimum with a good approximation, I guess. But I need to verify. Yeah, Max-CUT, at least that's true. And maybe, Sasha, do you think that's right? Whatever I said?
Yeah, that's true for all Max-CSPs or all alphabets, yeah. Cool. You can just sample essentially n over epsilon square random constraints, and that would be sufficient for 1 plus minus epsilon approximation.
Cool.
Okay.
Okay, great.
Santhoshini again. I'll take us offline and we can keep hanging out. But okay, thanks again.
Okay, sounds good.